we can calculate the equilibrium concentrations from the known equilibrium constant. And this is useful in many situations. You've got this reaction mixture, and you know it's going to go to equilibrium. You want to know what the concentration of the reactant is or the product is at equilibrium. You don't have a good way of monitoring or measuring that concentration, so you can predict what it is from the equilibrium constant. These sorts of calculations are not super precise, but generally we don't need really precise answers, we just want close. So there are basically two types of problems. If we know the equilibrium constant and all but one of the equilibrium concentrations, this is pretty easy. We've got the equilibrium constant expression. We just plug the known values in and solve for the one that's unknown. Okay? A more common situation is where you've got an equilibrium constant and you have initial concentrations and you don't have any of the equilibrium concentrations. Don't know any of them. And this is where ice tables. Remember that song? Ice, ice, baby. Dun, 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 dun. Yeah. Okay, let's do this example. Diatomic iodine decomposes at high temperature to form iodine atoms according to this reaction. In an equilibrium mixture, the concentration of I2 is 0.1 molar. What is the equilibrium concentration of I? Well, let's write the equilibrium constant expression. So Kc is going to equal the concentration of the atoms squared divided by the concentration of the molecules. So we have the concentration of I2, we know what K is, and we're asked to find the concentration of I. So this is one of the first types of problems, where we know Kc, we know I2, we're trying to find I. We can just rearrange the equation. So I squared, let's try that again. So I squared will equal Kc times the concentration of I2. To get the concentration of I, because we don't want the square, we want just I, we need to take the square root of both sides. So this will equal the square root of the equilibrium constant, 0.011, times the equilibrium concentration of the I2. I'm getting 3.3 times 10 to the minus 2. What's the unit on that? Molarity. Because all of our concentrations are in moles per liter. Bless you. So that could also be written as 0.033. Any questions? Exactly how you rearrange the equation and solve for that is kind of up to you. Just make sure that your math is correct. Bless you again. More commonly, we have the second type of calculation where we've got the equilibrium constant, we have initial concentrations or pressures, and we don't have anything about the equilibrium concentrations. So this involves a specific procedure. We're going to set up an ice table and record the initial concentrations. Then we're going to fill in the change row in terms of x, because we don't know what the change is. So we're just going to put it in terms of x, and the stoichiometry has to be taken into account. Then you add the initial and the change rows to find the equilibrium concentrations in terms of x. So you're going to get a concentration for each species, but it's going to have x's in it, because we don't know. And then we plug those into the equilibrium constant expression, and solve for x. So, simple example. Now back to this a goes to 2b. Equilibrium constant is 0.33. Initial concentration of A is 1. But we don't know anything about the equilibrium concentrations. So initially we have 1 molar of A and 0 of B. We don't know how much it changes, but we know that this goes down and this one goes up. So this goes down, if this one goes down x, that one increases by 2x because we get 2 moles of B for every mole of A. Okay with that? So we do the change in terms of x, and then we add these together. So we've got the initial concentration of 1 minus x, and so we write that as 1 minus x. And then for B, we've got 0 plus 2x, and that's 2x. Now we take our equilibrium constant expression. C equals, it's going to be B squared over the concentration of A. So K is 0.33, and that's going to equal B squared, so that's 2x, the quantity squared, divided by the quantity 1.0 minus x. Solve for x. The worksheet we're going to do in lab this afternoon is going to help you learn how to use the solver on your calculator. You can do these using algebra, and if you're comfortable with that and you like doing that, you go for it. But I'll show you that your calculator can do it much faster with a lot less thinking. Okay? This one's relatively simple, so, well, it's still going to end up with a quadratic. Yuck. So, pardon me? Solver. I'm going to use the solver. Because, I know there's a quadratic equation and you can solve these things. But when you have a calculator to do it, why? There's no good reason in my mind. Yeah. So I'm going to put this into my solver. I'm going to do 0.33 equals the quantity 2x squared divided by the quantity 1 minus x. And I'm going to tell it to solve. It takes a few seconds. And it comes up with 0.25. So x equals 0.25. There's more digits than that, but you get the idea. How could we check to see if this answer is good? Put it in here. Calculate k from it and see if it matches up. So let's do that. So I've got 2 times 0.25, and I've got that squared, divided by the quantity 1 minus 0.25, and that equals 0.33. So, bingo. Any questions? So we found x. Did we actually find an equilibrium concentration here? No, this isn't actually finished yet. The question doesn't even, well, there really isn't a question. It just kind of puts stuff out there. Let's assume that it's asking, what's the equilibrium concentration of A? Well, we know what x is. So the equilibrium concentration of A is going to be 1 minus 0.25, or 0.75 molar. And the equilibrium concentration of B is going to be 2 times x, 2 times 0.25, which is 0.50 molar. You can also check by sticking those numbers in. So 0.5 squared divided by 0.75, still 0.33. Any questions? Let's do a real one. Here's this reaction. Reaction starts with only the product and no reactants. Find the equilibrium concentrations of all three of the things. So I'm going to still use that, even though it's kind of high above. I'm still going to use that as my labels. I, C, and E. Initially, we just have no 0.0100, and these guys are 0. Okay with that? Now, we're going to do the change row in terms of x. It's going to be simpler if you start with something that has a coefficient of 1. So N2 is going to increase by a factor. It's going to increase by x. So this is going to be plus x. And O2 is also going to be plus x. If we were to calculate QC for this reaction, what would it be? It'd be this concentration squared divided by these two, which are 0. So it would be infinite, right? So that's way bigger than K. So that means it's going to go to the reverse. So these are going to increase. This one's going to decrease. How much is it going to decrease? Minus 2x. The 2 there is because of the coefficient. So at equilibrium, I've got x, x, and 0.0100 minus 2x. Equilibrium expression, NO squared divided by N2 and O2. Is that a question or are you stretching? Okay, so we've got, the question is why are these plus x and the others minus? Initially we're starting with no nitrogen and no oxygen. It can't go lower than that, right? It can only go up. So the reaction must be going in the reverse direction where this is reacting, decomposing to form nitrogen and oxygen. So this concentration is going to decrease and these are going to increase. Kind of a neat thing, if you get the signs on those exactly backwards, it'll still work out. X will just be a negative number. And then when you add your negative number, you're subtracting. So equilibrium expression, and I'm going to plug these things in. Actually, I'm just going to start. So here's Kc, I know what that is, 0.055. And that's going to be equal to my product, 0.0100 minus 2x squared, divided by my reactants, x times x. So you can do this using algebra and the quadratic equation. It's not my idea of fun, so I'm going to use my solver. 0.055 equals the quantity 0.01 minus 2x, that quantity squared, divided by x squared, wait for the solver. I'm getting 0.0057. Is that a possible thing? The thing with quadratic equations is there's often two answers, right? So I got this answer. If I plug that in for x here, quit, 0.01 minus 2 times 0.0057, I end up with a negative concentration. So that is a root of this equation, but it's not one that can work. It's not the solution we're looking for. So, nope. So what do I do now? Well, some calculators you can put boundaries on your answer for the solver, and others you just have it start with a different number. I let it start with the previous result, which obviously didn't work very well. So I'm going to go back to that and solve it by typing in 0 for x and seeing what it gives me. Okay, so this is a little nicer. X equals 0.0045. Well, 4475. Is that one going to work? Well, let's try it. 0.01 minus 2 times 0.004475. Yeah, that gives me a positive number. So this is my x. I have to use x to figure out what these concentrations are. In this example, nitrogen and oxygen ended up being x. So the concentration of N2 here is equal to the concentration of O2. And they're both equal to 0.00. I don't know why mine is slightly different than what the book is saying. And then the concentration of NO, I'm going to take this value and plug it into this expression, and I come up with 0.0011. Bless you. Or 0.00105. You can check those numbers by sticking them into the constant expression there, 0.00105 squared divided by 0.00448 squared. I'm coming up with 0.0549. It's supposed to be 0.055. That's very close. It won't come out exactly all the time. Any questions? Yeah.
You said you're going to show us during the lab how to do.
Yeah, we are going to work on learning how to do solving on a calculator in lab. Any other questions about this one? Sure. Okay, so here's another reaction. The reaction mixture at 100 degrees Celsius initially contains only the reactant and no NO2. Find the equilibrium concentrations. So we need an ice table. So I, C, and E. Initial concentrations are given. The reactant is 0.0250, and the product is 0. We fill the change in using X. So this one must be going down, and that one must be going up, because there's no option. So if the N2O4 is decreasing, this has a coefficient of 1, and so I'm going to use the X with this one and say its concentration changes by minus x. Then this one must increase by 2 times x. Once I have those changes in place, then I just add to get the equilibrium. So I'm going to use the equilibrium constant expression, Kc equals NO2 squared divided by N2O4. My constant is 0.36. So NO2 is 2x, and so that quantity is squared divided by 0.0250 minus x. So breaking out the solver again, 0.36. The great thing about these solvers is, you just type it in as you wrote it here. You don't have to do any rearranging or anything. So that time I came up with 0.0204. So I've got a value of x of 0.0204. Which is not matching up with the answer. So I'm going to go back and look at that and see if I typed something in incorrectly. Now 2x squared divided by 0.025 minus x. That's what it says. I try running it again, and I get x being a negative number, which that's not possible. Pardon me? You did? Awesome. I don't know why it's not matching up with this, but oh well. Oh, it is. I'm just having a brain fart. Okay. So you can get 2 roots. The other root's negative, so that one's automatically out. So here's my x. So concentration of N2O4 is equal to 0.025 minus x. Which is 0.0046. And the concentration of NO is going to be equal to 2 times x. Which would be 0.0408 or 0.4041. The answer in the book says 0.005 and 0.041. So, any questions?
So is x correct?
That x is correct, yeah. I just was second guessing myself. We can also do this with pressures. So we had a Kp where we looked at the equilibrium expression in terms of pressures. It's important that the pressures are in atmospheres. So here we have a reaction between gases The reaction initially contains both reactants, each with a partial pressure of 0.10 atmospheres, no product. Find the equilibrium pressures of all three substances. Exactly the same process. We're given Kp, we're going to use Kp, and then when we get our answers, the unit is going to be ATM instead of molarity. So ice table, ICE. So the initial concentrations are 0.150, the pressures, atmospheres, and there's no product, so that one's 0. Is this reaction going to go forward or in reverse? It's going to go forward because it can't go in reverse. There's nothing here. So this one's going to change in the positive, and these two are going to change in the negative. Use one of these to be x because the coefficient's 1.
So if we were given an initial value for the ICL, then it could go forward.
Yeah, if this was, maybe we had 0.150 of all of them, it would be hard to predict. You'd have to calculate QC and compare it to QP, well, QP and compare it to KP to decide which direction. Or you can just pick one, put your x in, and if x is negative and it still gives you positive concentrations or pressures, then it's okay. If you only had product and no reactant, then it would have to go in the reverse. So I'm going to say this is plus x and this is plus x. No, minus. We just talked about that. Minus x and minus x. And then what's the change for the product? Plus 2x. So at equilibrium, that one's 2x. This one's 0.150 minus x and 0.150 minus x. So Kp is the pressure of ICL squared divided by the pressure of I2 times the pressure of Cl2. So 81.9 is equal to 2x, the quantity squared, divided by 0.150 minus x, times 0.150 minus x. So you can call that squared. So in my solver, 81.9 equals the quantity 2x squared divided by the quantity 0.150 minus x, the quantity squared. And we're waiting in suspense. It's telling me that x is equal to 0.1229. So that means that the concentration of I2 would be 0.15 minus 0.1229. And that gives me positive pressure at the end, so that's okay. If this was larger than 0.15, then it would not be a possible route. It could not be the correct route, I should say. So the pressure of I2 is going to be 0.150 minus 0.1229. I'm not using my space very well.
I got only 0.129.
You got
I got, 0.129.
0.129?
Yeah, it's 0.1229.
Well, let me check.
I mean, I'm probably wrong.
but
Well, no, because I did this yesterday and I screwed it up. I could look at the answers while that's solving. The other one I'm getting is 0.192, which does not work. This is number 11. Yeah, it's supposed to be 0.246 for the pressure. 2 times 0.1229. Yeah, I think mine's right. But I got something not quite right yesterday. Got to make sure that the 2 is also getting squared. That was my mistake yesterday. So this comes out to be 0.0027 atmospheres. And the pressure of the Cl2 is going to be the same, 0.0027 atmospheres. And the pressure of that product is going to be 2 times X, or 0.246 atmospheres. Any questions? So if you don't have a solver, problems like this can be pretty tedious, time-consuming. Sometimes we can make approximations that make things go a lot faster. So we can simplify the calculation without losing accuracy, and that sounds like a win-win proposition. So if K, the equilibrium constant, is small, that means that the reaction does not proceed very far to the right. If your initial reactant concentrations are large, then we can assume that the change in them, X, is small. And so the initial concentration of reactants is essentially unchanged. It does change, but it may change by such a small amount that if you consider significant figures, it doesn't change it at all. Okay? So we can try this when K is small and initial concentrations are large. We check our assumption at the end by comparing the calculated value of X to the number it was subtracted from. That should be 5% or less in order for the approximation to be valid. So the X is small approximation. So here's our familiar A to B reaction. This time K is 3.3 times 10 to the minus 5. So this is a lot smaller than ones we've been dealing with, like 0.33 or 81.6. This is a small K. Initial concentration of the reactant is 1 molar. That's pretty high. B is 0. What are the equilibrium concentrations? Well, we can make the ice table. We're starting with 1 molar. That's going to decrease by X. B starts with 0, and that's going to increase by 2X. And so we have 1 minus X and 2X. But now what we're going to do is we're going to say, well, let's assume that X is small. If X is very small compared to 1, then this X, subtracting X doesn't change it at all. So the X is small approximation says, well, this goes to 1.0. Because X is so small that subtracting it from 1 doesn't really make much difference. Now, that bothers some people. So in Wrigley, there's a lot of semi-trucks full of fruit. So it's orange season. So here we've got a truck full of oranges, and you go on the scale and you weigh it, and then you're pulling away and one of the oranges falls off. Is that going to affect the overall weight of that load of oranges? No. It's so small in comparison to the whole thing that it doesn't matter. So that's what we're talking about here. X is so small, it doesn't matter. Now the X over here is going to matter because even if X is small, there's going to be some B that gets formed. So we can't just ignore all the X's, but we're going to ignore the X's that get subtracted from things, especially from much larger things. So we're going to put in into our equilibrium expression, we've got b squared over a. So 3.3 times 10 to the minus 5 equals the quantity 2x squared divided by 1. That would be much easier to solve without a solver, wouldn't it? So this one, we can just take the 3.3. There's a couple ways you could do it. I wrote that wrong. Sorry. The square's on the outside of the parentheses. So that's the same as 4x squared. We can take our 3.3 times 10 to the minus 5 and divide it by 4. And then we need the square root of that. And so x ends up being 2.87, well, let's call it 2.9 times 10 to the minus 3. Yeah.
We can assume x is incredibly small when our k value is incredibly small? Or
Yeah, you can only do this when k is small.
Okay.
When k is small and your initial concentrations are fairly large.
Okay.
If this initial concentration, was times 10 to the minus 7 or something, you can't do it.
Okay.
And you can always try it, but you have to check it. Okay? So the check here is that we want to look at x relative to the thing that we're subtracting it from. So the difference here, 1 minus 2.9 times 10 to the negative third, is 0.997. Wait, I did that wrong. We don't need to do that. Scratch that. We're wanting x to be less, 5% or less than the number we're subtracting it from. So we're going to take 2.9 times 10 to the minus third and divide by the number we're subtracting it from, multiply by 100, and that needs to be less than 5. Oops. Try that again. So that ends up being 0.29%. Because x is less than 5% of the number we're subtracting it from, the approximation is valid. So then we say that the equilibrium concentration of A is 1 molar. The equilibrium concentration of B is 2 times x. 2.9 times 10 to the minus third times 2. 0.0058. So to A, losing the orange doesn't make any difference. But for B, who didn't have any oranges, getting the 1 orange is a deal, right? Oh, I have an orange, right? So it's relative whether it matters or not. Does that make any sense? So you can do the x's small. It'll make the math much simpler. But then you take x, divide it by the thing you're subtracting it from, and find out if that is less than 5%. If it's more than 5%, you cannot use the x is small approximation. It'll mess your answers up. Any questions? Let's do an example. I think, okay. We're just going to plunge through and we're just going to finish this section. There's only 3 slides. So here we've got a decomposition reaction. We're given a equilibrium constant. This is a small equilibrium constant. So reaction mixture contains 0.1 molar of the reactants and none of the product. Find the equilibrium concentration of S2. Oh, it's got one product and one reactant. Never mind. Okay. So I'm going to make my table. Ice. So initially H2S is 0.1 and H2 is 0.1 and S2 is 0. So I'm going to put the change in terms of X. Since there is none of this product, the reaction must be going in the forward direction. So S is going to increase. It's going to increase by X. If this increases by X, H2 increases by what? 2X. So this is plus 2X. That was a messy one. That's a 1. And what does the H2S decrease by? 2X. So it's minus 2X. So we've got 0.1 minus 2X, and we've got 0.1 plus 2X, and then the concentration of our sulfur is X. So we have fairly large, reasonable concentrations anyway, of the reactant here, and we have a small equilibrium constant, and so we're going to try the X's small approximation, saying subtracting 2X from this or adding 2X to that doesn't matter. So we're going to call this 0.1, and we're going to call this 0.1. So Kc equals H2 squared times S2 divided by H2S squared. 1.67 times 10 to the minus 7 equals 0.1 squared times X divided by 0.1 squared. So X ends up equaling the constant. So we need to make sure that this approximation is valid. X came out to be this number. We're subtracting it from 0.1, we're adding it to 0.1. We're going to compare this. This needs to be less than 5% of 0.1. And you can see it is. What does that end up being? Let's see. I should be able to do that in my head, but 1.67 times 10 to the minus 4%. No problem. So our answer then, where can I put it? Put it down here on the left. The equilibrium concentration of the S2 is 1.67 times 10 to the minus 7 molar. Any questions? Yeah, and then I forgot the times 100 to make it 100%, to make it a percent. Yeah, the math didn't work before. Any other questions? One more. Here we've got that same reaction, right? Here we're starting with an H2S concentration of 1 times 10 to the minus 4 and none of the products. We have a small equilibrium constant, but this time the reactant concentration is small. We're going to try X is small anyway and see what happens. So the H2S is 1 times 10 to the minus 4, and these are 0. So the S2 will increase by x, the H2 will increase by 2x, and the H2S will decrease by 2x. You getting the hang of that part? Sort of. What I'm going to do is, I find it easiest to look at one of these that has a 1 coefficient, an unwritten coefficient. And I'm going to call that change x. And then I just apply the coefficients to the other ones for their changes. I could choose this one as changing by negative x, but then this would be plus 1/2 x. And I think it's best to not get into fractions unless you have to. A friend who teaches middle school math, and she says fraction is the F word. Okay, so 1 times 10 to the minus 4 minus 2x, and then this is 2x, and this is x. Kc is h2 squared s2 divided by h2s squared. 1.67 times 10 to the minus 7 equals. Now, if we're going to do the x is small approximation, then we're going to say that this is the same as 1 times 10 to the 4, minus 4. That subtracting 2x isn't going to matter. So my H2 concentration is 2x, and that gets squared. My S2 concentration is x, and I'm assuming x is small so that my H2S concentration is 1.0 times 10 to the minus 4, and that's going to get squared. This is going to end up being 4x cubed over 1 times 10 to the minus 4. So this can be solved without a solver. You can still use the solver, though. 1.67 times 10 to the minus 7. Yes, it is. Thank you. I wrote it the first place and not the second place. Then I'm going to multiply by 1 times 10 to the minus 4 squared, and divide by 4, and that's going to give me the value of x cubed. So what I'm coming up with there is that x cubed is equal to 4.175 times 10 to the minus 16. So then I'm going to take the cube root of that, and I end up with 7.5 times 10 to the minus 6 is x. Well, leave this off. So let's compare that to this concentration. So I'm going to take that x value, and I'm going to divide by 1 times 10 to the minus 4. And then I'm going to multiply by 100 to make it into a percent, and I get 7.5%. X is 7.5% of what I'm subtracting it from. That's larger than 5. We can't use x as small. So how does that change things? Well, what I'm going to have here, instead of just 1 times 10 to the minus 4, I'm going to have 1 times 10 to the minus 4 minus 2x. So I'm going to put the changes in here in blue. Minus 2x. And for that, I'm going to use my solver, because that's really, that you can't even do that with the quadratic equation, because it's got a cube in it. Is there a cubatic equation, or I don't know what you'd call that. 1.67 EE minus 7 equals the quantity 2x squared times x divided by the quantity 1 EE minus 4 minus 2x, and that quantity squared. Waiting in suspense. So 6.78 times 10 to the minus 6. Yeah. So this number is not hugely different than what I got from the X's small approximation, but it is different. So then what's our equilibrium concentration of S2? It's X, right? Nailed it. Book says 6.78 times 10 to the minus 6. Any questions? So you're welcome to try X is small on all of them if you want to, but you have to check. If X is more than 5% of what you're subtracting it from, you can't do the approximation. So these are just some notes. Concentrations must be expressed in moles per liter. Could you have a problem where they're trying to trick you and they gave it to you in milligrams per liter or something? Yeah, could happen. You got to convert it then. If you're doing pressures, partial pressures have to be in atmospheres. If they're given in anything else, you got to convert them to atmospheres. It doesn't work otherwise. Use the appropriate equilibrium constant, Kp or Kc. We looked at the relationship. It's possible you'll get a problem where they give you Kc, but you need Kp. You might have to convert it. You have to look at the equation and determine what's the change in the number of moles of gases, right? So we're usually using molarity, concentrations. Moles of substance can sometimes be used in place of concentration or partial pressure. But you can only do that when the moles of the reactants in the chemical equation is equal to the moles of the products. So if you're starting with 2 moles combined of reactants, and you're ending up with 2 combined moles of products, you can do that. Otherwise, no, you can't. And the X is small approximation does not mean that X is 0. It just means that X is so small that we don't have to consider when it's being subtracted from something much larger.